we can start then. Yeah, so today is part 2 of the IPhO Livesolve, and me and Prolector will be starting from problem D1 of theoretical question number 2. So yeah, let us start. I guess we can reread the question. Okay, I can read it. The model of considered above was idealized, and we assumed that the ring was charged instantaneously. In reality, charging is non-instantaneous, as a ring is a capacitor with a finite capacitance C. In this part, we will analyze the properties of this capacitor. You might need the following integrals, and part D1 is to calculate the capacitance of the ring, and the ring has a finite width 2a, and a is much less than r. So yeah, I don't really have much more of an idea compared to last time of how to solve this.
Yes, I also don't have any idea.
Yeah, I guess we can just draw it again. Maybe
Yes,
it's like this is the ring.
okay.
Oh yeah, and then uh
Are you audible in the stream? As I can't hear your sound from the stream. I have opened it on another tab.
oh, you can't hear me.
I can hear you from the Zoom, but I can't hear you from the stream.
Oh, one sec. Let me see if my voice is just too low. Okay, I can try increasing. Okay. Okay, if you guys can hear me now, then tell me. Okay, they can hear.
Okay, so we can continue this problem.
Yeah.
This is cylindrical uh, this is cylindrical wire and looped around in a circle. So we have to find its capacitance. So for capacitance, we charge it with a voltage something V,
Yeah.
and the charge induced on it.
So that would introduce a negative or positive charges on the ring.
Yes. Or we can integrate the field from 0 to infinity. So we can find the potential. Because we know rings z-axis formula, and we can just take the element of the cylinder as a shape of ring.
Yeah, sure.
So let us take an element at a random distance r, but the element will be curved, so we have to take projected area, or No, we have to take this area. Wait a minute. This is a cross section of this wire. Then if we take an element at theta from here, then we have this A, and this element would be A into d theta.
Yeah.
So the total charge would be sigma A d theta into this area, which is 2 pi r plus A. A, no, A minus A cos theta. I am not sure about this step because do we have to take cross section or we can take complete?
Probably cross section, because if you take complete, I feel like there'd be some other contributions.
Also, there is one problem for the ring above the plane. Their z equals to 0 would also occur above the plane. So if we also we can't integrate from this because this will give the potential difference between this and infinity, but we want the potential difference between this. So I guess this method won't work.
Okay,
Also, this question was haunting me whole night. It was coming in my dreams, but I was not able to solve.
yeah, this is kind of tough.
Yes, and points is also given very high for this question.
Yeah, has there like been a 2-point question other than this? I don't think so.
No, there was one which had a lot of calculation.
Oh yeah, the last part of T1.
Yes. I think we can continue SC and do the next part.
Yeah, sure. We can just skip.
Yes.
Yeah, apparently in the Discord they told us that the rest of the rest of the part D can be done without D1.
Okay. So let's do D2. Determine the dependence of the charge on the ring as a function of time, Qt, and make a schematic plot of the dependence. T equals to 0 correspond to the time moment when the electrons are in the plane of the ring. What is the charge on the ring Q naught when the absolute Qt is maximum? The capacitance of the ring is C. That is, you don't have to use actual expression found in D1. Remark, the drawn polarity in figure 3 is for indicative purpose only. The sign should be chosen so that lens is focusing. I guess I forgot to read the upper part. When the electron reach the active region, the ring is connected to the source V naught. When the electron passes through the active region, ring is connected to the ground. Okay.
Okay, so it's just going to be a RC circuit.
Yes. And charging and discharging both.
Yeah, so I guess you can just write Kirchhoff's law and get the differential equation.
Yes.
Uh,
So we have V
so the voltage drop on the resistor is just
I
R,
times R.
yeah. And then in terms of its charge, it's and then the voltage on the capacitor has some
Would be
charge.
Q by C.
Yeah, I guess you can say Q of T. And then that's going to equal to the original voltage. So
Yes, some of them will be equal to. And let's say the time tau be d by V for charging.
no, yeah. Okay, so then
dt. We can use integrating factor by multiplying R. I mean dividing R here and multiplying with e to the power negative RCT. E to the power negative RCT. E to the power negative RCT.
okay,
So here we have d cubed t times e to the power RCT by dt equals to V naught by R e to the power minus RCT. And then we can integrate from T0 to tau, and charge is 0, and let's say it becomes Q naught at tau.
yeah,
So after integrating we would get Q, wait, Q naught e to the power minus RC tau minus 0 equals V naught by R, and we have integrating factor minus RC. I think I have done something wrong. Yes, I have done this wrong.
oh the
Integrating factor was wrong. It would be 1 by RC instead of minus. So it would become dq by dt plus q by RC equals to V naught by R. So we have integrating factor as e to the power integral of 1 by RC dt. So we have e to the power t by RC. e to the power t by rc, to the power t by rc. So now we would have dq e to the power t by rc by dt equals to v naught by r e to the power t by rc. So integrating from t to tau and from here integrating from 0 to q naught, we would get q naught e to the power tau 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 by rc uh, equals to v naught by r e to the power tau rc minus 1. So we would get q naught equals to v naught by r 1 minus e to the power minus tau by rc.
Okay, that's yeah. I think that's representative or what I remembered for this type of.
So this would be charging process complete. Now we have to do discharging.
Yeah. So
Can you make another slide?
yeah.
So for discharging process, let's assume there is Q naught and we have resistor R and it is earth. So we would get the equation dq naught by dt C equals to R times, no, R into this would be Q naught by C, or negative, I guess. As this is voltage drop across the resistor and this is the voltage drop across the capacitor.
Okay. So then we proceed with a similar differential equation.
And it would be Q, instead of Q naught, it would be QT.
Yeah.
Here also QT. So we can integrate this to get e to the power minus, wait, let me write all. That would be dq by dt equals to minus q by rc. So we have dq by q equals to minus dt by rc. So we have from q naught to, should we integrate for general q or we directly put 0?
General.
Okay. So if we put 0 then it would be ln 0. So general would be ln qt by q naught equals to e to the power, no, minus t by rc, and this is t minus tau if we take from the starting t.
Yeah. So that
Therefore it implies q of t would be q naught times e to the power minus t minus tau by rc for discharging.
okay. So it can. Okay. Then you have all the possible values of the charge. And then we have to draw a plot for the dependence.
Yes, so we earlier got we know. Okay, I have wrote it down. Can you bring to third next slide? One more.
Oh,
Can you go to next slide? Yes. So we have Q as a function of time, that is V naught by R e to the 1 minus e to the power minus t by RC for t less than tau. Here tau is d by V. And for t greater than tau, we have Q naught into e to the power minus t minus tau by RC, where Q naught is V naught by R e to the 1 minus e to the power minus tau by RC.
yeah. So I guess it's going to be decreasing and then increasing again.
No, increasing and then decreasing.
Oh,
Because first charging process is done. So it should increase.
okay.
So if we plug 0 here, then it would be 0 and would reach, would concavity be upward or downward?
It would be downward, right?
So
Because,
first till Q naught, it will be like this.
yeah. And then,
And then it would decrease like this. Q is a function of time.
okay. We can ask chat if this is correct. Okay. Stream is a bit behind actually.
Yes.
Okay, no one's really saying anything. So maybe you can just go on to D3.
Okay.
There's no D3, it's just E1. Okay. In this part of the problem, we'll consider the action of this more realistic lens. Here we will again neglect the width of the ring 2A and we'll assume that electrons travel parallel to the z-axis before reaching the active region. However, the charging of the ring is no longer instantaneous. Find the focal length of the f of the lens. Assume that f over v is much greater than r0c, but d over v and r naught c are the same order of magnitude. Express your answer in terms of the constant beta from part B and other known constants. So I guess, first of all, the force that we got from yesterday was like 2e beta q. And then for this case, q is going to depend on time.
Yes, Q is depending on time.
Yeah. F over v is much greater than r naught c. So I guess that means that when the electron is like charging, it doesn't really change in its position. So r would be like constant at that point of time because of f over v much greater than r naught c.
I don't understand. So what would be constant?
R would be constant.
This R or this R?
Yeah, this r.
Okay.
Yeah, so then it'd be.
It was also earlier also it was constant.
Yeah, I think it's just to make it more simpler. Otherwise, like you would have to double integrate or something.
Yeah.
Okay, so then I guess we can do the same way that we did the other part when we found the focal
Yes.
length. So like find the velocity of the electron, and then
Yes. Y-axis velocity.
yeah.
E beta. But in this part, we have the electron would first enter. While entering, we could do simply what we earlier did, but while exiting also, it will also attract. So, should we neglect that, or we have to calculate that part also because charge would be there?
No, yeah, that's true. Let me see.
Okay, I guess here this can help because V is so fast. V is slower. Wait, no, this can't help.
It says d over
But
v and r naught c are in the same magnitude. So
D over V is approximately equals to R naught C.
does that doesn't really do anything though.
Yes. Or we can just calculate, and if this quantity, if we see, then we can neglect it mathematically instead of physically thinking.
Sure.
So here we would get E to beta R into Q. And Q was V naught by R 1 minus E over minus T by RC. So we can integrate from V0 to V equals to something Vy, and from time t0 to time d by v. So
Yeah.
after integration, we don't have Vy term, so we can directly substitute Vy here. 2t beta r v naught by capital R constant. So integrating this would get d over v minus plus rc times e to the power minus d by v minus 1.
Okay, so then V of I would be.
Okay, here I forgot rc. Okay, so here this come into existence. This is almost comparable to 1. So this won't neglect.
Oh yeah, so D over V and RC are comparable. So like
Yes.
that could simplify if we approximate.
Okay, if we apply similarity for this, then we would get F over V RC. So that would result in infinity, and that would give us 0. Or am I doing something wrong?
Right, so what do you want to do?
I am applying similarities dvy over dt equals to q naught e to the power minus t by rc from t equals to 0, and there is Vy equals to Vy. Let's say this Vy naught and then Vy dash. So we have some general time t,
Oh yeah.
and that here the t would be f by v. So if we integrate this, we would get, okay, we will still get one term, so we have to integrate. So we have m vy dash minus vy 0 equals to q naught 1 minus, wait, let me integrate this properly, rc by minus 1 e to the power minus t by rc from limit 0 to t. So if we put t, we will get this, and if we put 0, we get 1. So we can write this 1 minus t over rc. So now we got a function of Vy. So uh, we know the total Y, so we can integrate to get the focal length.
Yeah, so add both functions. We can go to next page. So like the end velocity is Vy, or what is it, Vy prime? I guess the Vy prime comes from these two, right?
We have Vy prime minus Vy naught equals to Q naught RC 1 minus e to the power minus t by RC.
Okay, so that's the change in velocity.
Yes. So we have zero velocity here. Then we wait. This is something above. So we have zero velocity here. Then when we go here, we get Vy 0. And for general time here, we have Vy dash. So we have to find where this y coordinate intersects the x-axis. So we have to find the time at which y is 0. And at that time, we can directly multiply by x-axis velocity to find focal length.
Okay, so just set this to 0.
No, we have to write it as dy by dt minus equals to Vy 0 plus Q naught RC 1 minus e to the power minus t by RC. And then integrate it from R to 0 and from time 0 to t.
Okay.
So here we get negative R. We get V. I guess here we should have minus dy by dt. So negative would be cancel out because Vy we have chosen in negative y direction. So we would get Vy 0 times t plus Q naught RC times t minus and this integration.
Cr e to the negative t over RC.
What did you say? Can you write it down? Integral.
So then yeah, that should be right.
Okay, so if we put the limits, we get 1 minus this. 1 minus. So we have R equals to Vy 0 t plus Q naught RC t minus RC 1 minus e to the power minus t by RC.
Alright, yeah.
And what was the value of Vy0 and Q0?
We'll go back to the last page.
So Vy0 is 2e beta r V0 by mr d by v plus rc e to the power minus d by vrc minus 1. And we have Q0 as, we have to go one more slide back for Q0. Yes, Q0 was V0 by R, 1 minus e to the power minus tau by RC. Okay, so I have copied all three. So we have R equals to Vy0 T plus Q0 RC T minus RC 1 minus e to the power minus T by RC, and Vy0 as 2e beta RV not by m r d by v plus rc e to the power minus d by v rc minus 1, and q0 as v naught by r e to the 1 minus e to the power minus d by vrc.
Yeah, that looks right.
Okay, so we have to find t from these three equations. I guess we can neglect this term
Which one?
because or we can't solve both linear and e to the power term.
Oh, let me see. D over V and R not C are same. Yeah, that should be neglectable then, because that means that they should go to 0 or approximately to 0.
But this is not 0. We have t very big. So this would be almost infinity. So we would, okay, we can't neglect this, but okay, we can neglect this part. And for this, I don't think we can neglect, as this will be almost 1. So it would be 1 over e minus 1.
Wait, but e to the negative d over v are not c.
Because they told d over v pi rc is almost 1.
Yeah, so then that should be, oh yeah,
1 over e. So we can't neglect this term, but we can neglect this e to the power minus t by rc term, as t is very high because f is very long.
yeah, okay.
So we have t as r plus q naught r square c square by Vy0 plus q naught rc, and substituting the values of this would become very ugly. This is our T. I think we have done something calculation mistake or this would become very ugly.
Well, you can look back.
Sure. Can we go one more slide back? Okay. So here we have find Vy0 by charging process. So charging integral is also very ugly.
Okay.
For discharging, can we assume Vy0 to be constant?
For discharging, yeah, I think so.
Then we can solve it little bit easily.
Okay, then we can try that.
Yes. So we have Vy0 to be 2e beta r V0 by mr d over v plus rc e to the power minus t by v over rc minus 1. So we can directly write time as r by v y0. So therefore we have focal length to be v0 into r by vy0. That is mr by 2e beta 1 over d by v minus rc 1 minus e to the power minus d by vrc. So we are getting focal length as this if we assume discharging to be constant.
Yeah. Let me see.
So anyone in the chat can verify this, please. Someone is asking which problem is this. I will go check.
It is
Yes.
theoretical 2.
Part E1. Someone is saying isn't correct. The answer is termed in the terms of E. What is E?
Energy, I think. Is that?
But our V naught term got cancel out.
can look back.
One more slide back. So we have F is equals to 2E beta R Q, and Q is, oh, I guess we have messed up voltage and velocity, because I have wrote both as V0. This is capital V0.
Oh, yeah. So this should be voltage, not initial.
Yes.
Then we can, we can just go back and fix that.
Okay, so this is V0, capital V.
And then focal length is,
This is small v only.
yeah.
So we have M R, M capital R by 2E beta R V0 by V0.
And then this one will go up too.
Yes. So this would become here V, and this would become square. So this would become E. But also we have velocity terms here.
Yeah, I guess that will go up too.
And what about this?
Oh yeah. I don't know how to do it like that.
Or can we ask the chat if this is the correct answer or not?
Okay, is this the correct answer?
They are saying there is no exponential denominator.
Okay, then maybe.
We can neglect it.
Yeah. But why? Why would we neglect that?
Yes, that's my question also. Because they have said D over V is comparable. So if answer is this, then they have neglected the term of exponent. Chat, can you verify if this is the correct answer of focal length or not? This is voltage. Also, they have explicitly written that D over V is not comparable. So here also, if they compare this and this, then also it is comparable.
Yeah.
Or if this cancel out, if we plug the discharging process. But this in the discharging process there are a lot of extra terms. So I don't think it would be it would cancel out.
They're saying this is an incorrect answer.
Oh,
Apparently it's
then
not
we
dimensionally correct.
no dimension. Wait, this energy is mv square. This voltage by resistance is current. By is charge. What is beta dimension?
Oh, you have to go back, I think.
Or yeah, we can say 2 beta E R 2 beta ERQ was the dimension of
Oh yeah, beta is like k over r cubed or something like that.
this is potential energy. So Q2. So this is force dimension. Okay, so we have the charge dimension wrong because current will cancel out by charge leading to only time dimension, but beta will still have the dimension of inverse charge.
Oh,
So we have
maybe.
to eliminate.
Maybe there's like capacitance too.
Oh, we missed capacitance term.
Yeah, there should be like some C or something in that order down there.
Should we do the all calculation again instead of just rechecking it?
Yeah, we can do that.
So we have F is equals to 2 beta Q. Here Q is electron. 2 beta E R 2q beta r. 2q beta r. Yes, this is F. So M dV. Oh, this is oh, wait. Do we have to multiply charge of electron as well, or
Yeah, I think so.
okay? Then I guess dimension would be correct of the previous one. Still, we can do it again. So we have here 2 beta. Let's call this as a constant k. So we don't have to write it again. And k is equals to 2 beta e.
Or you can do 2 beta E over M.
Okay. M also we can remove.
Yeah.
So now we can plug the function of the q. So we can get q as a function v naught over r. It's the dimension of current. Okay, we have calculated q also wrong. The q naught dimension is of current, but it is a charge. So this would, I guess, become Q naught C times 1 minus e to the power minus dt by RC.
Okay, then the capacitance would be in the denominator.
Okay. So we can integrate this to get Vy 0. So Vy 0 would be K times R times V naught times C d over V minus 1 minus e to the power RC. Okay, RC would be here. E to the power minus d by RCV. So we can get, if we ignore this term, we can get K R V naught C dV d by V equals to Vy 0. And we have focal length equals to time, and time is here V by Vy 0 into V naught, which is equals to V naught, and we can write V, so we can't. So we have RV square by K R V0 C D, and R gets cancel out. We can get,
MV
we can
square.
put M by 2 beta E. So we have E by beta E
Okay, is that correct? Okay, yeah, it is correct.
but still I don't understand why we can neglect this term.
Wait, did we add the charging and discharging charge?
No, we have done only charging and we neglected one of the terms in that.
Oh, maybe it gets cancelled out if we do both.
Okay, so let us try discharging also. Can you make another slide? Yeah. So for discharging, we have mdvy by dt equals to, or we can say directly dv by dt equals to negative of, no, here positive only, k times r times q of t, that is q naught e to the power minus t by rc.
Oh, and the chat says that they have taken an integral from d over v to infinity, which is why the exponential disappears.
Oh yes, I think they are correct because it will take a long time to reach the f. So
Oh yeah, because f over v is much greater than the characteristic time.
hmm, so we would get Vy minus Vy0 equals to A R Q naught. But here we have to find general time only. So we can get RC 1 minus e to the power minus T by RC.
Yeah, and then this goes to 0. Yeah, then that will work out.
No, it would get 0 after we integrate once more. So if we can write this as dy by dt equals Vy0 plus KR Q naught RC 1 over e to the power minus T by RC, and then we can integrate it again. So we get R equals to Vy0 into T, and we can substitute T as F over V. We get K R Q naught RC F over V times this integral would become negative
1 minus rc e to the minus f over v rc.
1 minus 0.
Okay.
So we can plug values of Vy0 and Q0 now.
Okay, I can go to the next slide.
Beta I had not completed copying. Can you go to text, right? It is R equals to Vy0 F by V plus K R Q naught RC F by V minus K R Q naught R square C square.
Okay.
So we can substitute R equals to Vy0 as Q2E beta R V naught. This is capital V naught F over M R V plus K. K here is 2 beta E by M times R by V RCF times Q0, which is V naught C 1 minus E over oh, I forgot to write this term D by V square plus 2E beta R V naught by MR RC to the power minus D by VRC minus 1. and this is T over RC, that is D by V RC. Okay, so this cancel out with this,
Okay.
and we get this.
Alright. Then that should be it for E1 then.
Yeah,
Okay, then we can do E2.
but this was nice question. I liked it.
Yeah, yeah, same.
You will see that the result of f is similar to that obtained in part C, whereby the values of q is substituted by q effective. Find the expression of q effective in the terms of quantities in the formulated problem. We not see.
So we
E2.
just compare the focal length. So like,
So they have told that the same expression is obtained in part C, but the q is replaced by q effective. So here q effective is V naught into C, because that replaces the term that we got in the focal length one, if I remember correctly.
yeah, okay, that should make sense. Then we should do T3. Wave-particle duality, which states that each particle can be described as a wave and vice versa, is one of the central concepts of quantum mechanics. In this problem, we will rely on the notion and just a few other basic assumptions to explore a selection of quantum phenomena covering the two distinct types of particles of the microworld, fermions and bosons. Oh, this is interesting. Like, I don't think there are many IPhO problems that do quantum or like modern physics.
Yes, but this is my most not favorite topic in physics, because
I guess.
I can't solve any problem of this topic.
Uh, yeah.
Though first part A of this seems like a INPHO 2019 problem.
Oh, there's similar. Okay. Yeah, we can read part A. Consider a
Yes.
particle of mass m moving in a one-dimensional potential well, where its potential energy is given v of x is given by the piecewise function 0, where 0 is less than x less than L, and then infinity x less than 0 or x greater than L. While a classical particle can move in such a potential having any kinetic energy, for quantum particles only some specific positive discrete energy levels are allowed. In any allowed state, the particle can be described as a standing de Broglie wave with nodes at the walls. Determine the minimum possible energy E minimum of the quantum particle in the well. Describe your answer in terms of m, L, and Planck's constant h. So I guess the potential well is just this. And then over here it's infinity, so the particle can't escape anywhere. And then there's like standing.
Yes, it will collide and bounce here.
Yeah. So the Broglie wavelength is just L is h over p, and p is the momentum of the particle.
So for ground state wave would look like this. standing wave would.
Yeah.
So this is lambda over 2, which is equals to L. So lambda would be 2L.
Yeah, and then E is P squared over 2M. So 2L, 2 lambda over H squared.
Oh, this is exactly INPH problem.
Oh, really?
This I thought it would be similar, but it is exactly same as INPH problem 2019. I recently solved it.
Oh, that's nice. Oh,
They also told us to find energy in such a region.
I think this is like standard result. Yeah, standard result. So
Yes.
this is H squared over, and this is 2, this is L, oops, over 8ML squared. Okay, and then we can do the next part.
Yes.
Yeah, you can read it.
Okay. The particle state with minimum possible energy is called the ground state, and all the rest allowed states are called the excited state. Let us sort all the possible energy values of in the increasing order and denote them as En. Starting from the E1 for the ground state, find the general expression of En.
Okay.
So we have n loops here.
Oh,
So we can do the same thing that we did in the part A1,
oh yeah, yeah.
but for this lambda.
So lambda here is 2L over N. So that would mean that using the same thing, E is just H squared N squared over 8ML squared. And then in terms of E min, no, yeah, you can just, yeah, this is just the general, double box. Okay, then A3. Particle can undergo instantaneous transition from one state to another only by emitting or absorbing a photon of the corresponding energy difference. Find the wavelength lambda 2 1 of the photon emitted during the transition of a particle from the first excited state E2 to the ground state E1. So I guess energy difference here is given as E2 minus E1.
Yes, and we can write energy as hc by lambda.
Yeah, and then we just equate that. So equal to hc by lambda. So lambda 2 1 is hc over E2 minus E1. Oh, and then E2 is, I guess you use the formula from that part. So E2 is 4hc, 4h squared over 8ml squared. Then E1 is h squared over 8ml squared. So that means that delta E is equal to 3h squared over 8ml squared. So lambda 21 is 8ml squared, mc squared, mcl squared over 3h squared, 3h.
Yes, part A was very easy.
Yeah.
So
Oh,
let us continue to part B.
okay, this looks
Part B.
harder already.
Yes. Optical properties of molecules. In this part, we will study several optical properties of cyanine, CY5 molecule, a widely used dye molecule schematically shown in the figure 1a. Its optical properties are determined mainly by the carbon backbond composed of alternating single and double bonds between the carbon atoms, shown in the figure 1b. While the influence of the ring at the molecules and as well as radicals are is much smaller, three of the four valency of carbon of each carbon and nitrogen in the back bond form the chemical bonds. Is this back bond or double bond?
Oh, in backbone.
But for back bond, I think it should be double bond because here is double that pi bond. For back bond, that is very weak bond NDF3 and such molecules.
Okay, sure.
Form the chemical bonds, while remaining valence electrons are shared and can move along the whole back bond. The net potential energy of each such electron is shown while oscillating thin line with in figure 1c, with the minimum corresponding to the position of C and N atoms. Okay. Figure A, chemical structure of cyanine molecule, the back bond of CY5 molecule, and the interatomic distance L, potential energy of electrons along the back bond thin line, and its approximation step function given in equation 1. I don't understand this part C. Rest I got. Well, I figure C. Can you explain figure C?
Okay, let me take a look at the problem.
What? Sorry,
I'm trying to figure out what figure C means too.
okay. For simplicity, we will approximate this potential energy profile by a simple function given in equation 1. What is equation 1?
Equation 1, oh, the thick line. So L equals 10.5L, isn't?
Oh, it is equation 1.
So I guess like figure C is just the potential energy interactions between each bond.
Okay. As a result, we obtained the electronic gas composed of 10 electrons, 7 from the C atoms, 2 from the N atoms, and 1 from the N plus ion. Okay, so are they saying that double bond electrons, 1, 2, 3, 4, 5, 6, 7. Yes, I think they are telling that electron gas is composed of all the double bonds electron. Moving in the one dimension potential well discussed in part A. In our evaluation, we can neglect the mutual interaction of these electrons. However, we should account for the fact that electrons are fermions and thus obey the Pauli's exclusion principle. We also neglect the influence of other electrons as well as motion of the nuclei. Okay. Evaluate the largest wavelength lambda for the photon that can be absorbed by the CY5 molecule, assuming that electron system is initially in its ground state. Express your answer in terms of small l, physical constants, and some numerical prefactor, and calculate the numerical value.
Okay. So that's a lot to take. Oh, so I guess the first thing is that there are 10 electrons and they follow the Pauli exclusion principle. So I guess they occupy the first 5 states because each state can take 2 electrons.
Yes.
So they want the transition from the 5th state to the 6th state.
Yes. To get the longest wavelength, we have to reduce the energy as much as possible.
Yeah, so you have like, oh god, that's a bad 6. So similar to the part A3.
Yes.
And then we just plug in the formula. What is it? So 36 h squared.
But what we will take as L length?
L should it be 10.5 L, like the width of the thing?
But one electron, okay, all of these are conjugation. No, the three of them are separate conjugation and the rest of them are in conjugation. So shouldn't we take the 1, 2, 3, 4, 5, 6, 7, 7 to be in one L and then 3 should be in another L because they won't enter into this double bond conjugation, so they can't move.
Oh, yeah, that's true. Yeah, I guess you can take it as just 7L.
But for that we don't have L also. Here for 10 they have given us 10.5 L. For 7 we should take 7 or 7.5 L, or we can't say.
Yeah, we can't really say. Because we don't know the exact distances. So maybe they want us to take 10.5? Or no, they say...
Yes. Also my chemistry is very weak because I don't know n the lone pair of n would participate in conjugation and make this connected or not.
Honestly, I think like since this is physics, they don't really want us to consider that. So maybe they just want us to take 10.5.
Yes. And that would be easier also to calculate.
Yeah. So then we have like 11 so this should be the answer.
Yes. So chat, is this the correct answer of B1 part B1? I think we should also write the number B1. But they have told us to calculate the numerical values. So what should we take as M?
Oh, we have to calculate numerical.
Okay, mass of electron, I think. That is 9.1 times e to the power minus 31. Sorry, 10 to the power minus 31. And also this is 10.5 L. Okay, you have taken L. 10.5 into, and L is here 140 picometer. 140 e to the power minus 12 squared divided by 11. I am getting it as 6.47. Wait, let me write one. 6.4748 times e to the power minus 7 meter. That is 648 nanometer.
Yeah, that seems on the scale of wavelength.
Yes, this is invisible section region.
Alright, the chat isn't really saying anything, so I guess we can continue.
Okay, but I was not sure about that 10.5. So, but what can we do?
Yeah, I guess we like when someone comes over and just checks, they can tell us. And B2. Another diatom, CY3, has a similar structure, while its backbone is shorter by 2 carbon atoms. Is its absorption spectrum shifted to the bluer or to the redder spectral region compared to the CY5 molecule? Evaluate numerically the magnitude delta lambda of this spectral shift. You can assume that removing 2 carbon atoms doesn't change the molecule shape and only makes the backbone length shorter by 2 interatomic distances. Yeah, I don't.
So this is the same question as P1, but we have to just reduce the factor. So
Is red shorter or longer wavelength?
red is 700 nanometer and blue is, but we have to calculate numerically. So I guess we should first calculate the wavelength. Also, red is 700 nanometer and violet is 400 nanometer.
Okay, and then it's shorter by 2 carbon atoms. So there will be 2 less electrons. And then the distance would be shorter by 2 interatomic distances. So L would be shorter 2 times. 2L.
Yes. Violet is 400 nanometer. So we have to calculate from n equals to 4 to n equals to 5.
Yeah.
And the distance would be 8.5. 400. So you can calculate that.
Okay. 9h squared over 8m 8l squared.
Instead of 8, won't it be 8.5 because we have subtracted by 2. So 10.5 minus 2 is 8.5.
Wait, what?
We have originally 10 L, capital L equals to 10.5 L. And they have told us to subtract it from 2 interatomic distance. So 8.5 L.
Oh yeah, 8.5. Okay, then I can just yeah. I don't have a calculator with me, so I guess you can
Yes, I
calculate.
am calculating it.
Okay.
It is 140 picometer. 140 times 10 power minus 12 square times H. H is 6.626, 10 to the power minus 34 divided by 9 divided by 3E8. But previously H was in the denominator. Now it become on the numerator. I think your expression is little bit wrong.
Oh, is it?
Yes. C would be in the numerator and H would be in the denominator.
Oh yeah. Alright.
So we get 518 nanometer, 519 nanometer.
So then it gets bluer.
Yes.
Okay.
Also, we have to calculate delta lambda. So delta lambda would be 47. Wait, 648. 648 minus 5 and 9, which is 129 nanometer. And this should be answer. If anyone is watching the stream, can you confirm it?
And there's only 2 people watching. And one of them is probably me.
And one of them is me.
Okay. We can just go to the next one then.
Okay.
Okay, you can read this one.
Being in the excited state, molecule can undergo spontaneous transition to the ground state while emitting a photon. The mean rate K of such event, that is relative decrease of the molecule being excited state. dN by over n over time dt is k equals to 1 over n dN by dt. Is determined by the wavelength of the emitted photon, the transition electric dipole moment d, which is order of d proportional to EL. Okay, this is dipole moment. Well, where here E is the elementary charge as well as vacuum permittivity, epsilon naught, and Planck's constant H. Using the dimensional analysis, determine the expression of the rate of spontaneous emission in the terms of epsilon naught, H, lambda, and D. The numerical prefactor of your expression is 16 by 3 pi cube. They have given 0.7 points for just dimensional analysis.
Yeah, that's weird.
So we have K, that is 1 over time dimension, epsilon naught, H, lambda, and D. D is dipole moment, which is P times L, which is Q times L. L here is meter. Lambda is also meter. Q is joule second, and epsilon naught is 1 upon 4 pi epsilon naught is into kg square. Okay, no, sorry. In Coulomb square by kq square by r square. Meter square equals to Newton, that is kg meter per second square. So that is meter cube and Coulomb square. So second square c square by kg meter cube. So we have joule. Joule is kg meter square per second. So we have this. So we have epsilon naught by d square equals to s per kg meter cube, and d square is meter square, so that is meter power 5. And we have only one kg term, so we have to multiply it by h. We get kg meter square by second square by second. So second gets cancelled out, and that becomes meter cube. Oops, I did some mistake.
Oh. So what are all the units?
Sorry, what?
Oh, no, never mind.
My second is cancelling out. Is getting cancelled out. But it shouldn't. Or I guess I have done calculation mistake in that part only. So I have epsilon naught h over d square. That is epsilon naught is S square C square by kg meter cube, and H is kg meter square over second, and D square is C square M square. So M square gets cancelled out, C square gets cancelled out. Okay, S is not getting cancelled out. Kg is getting cancelled out. We have S over meter cube.
Okay, and then K is
Want
1/2.
So we got a lambda cube to cancel out the meter, and we can do whole inverse to get 1/2 lambda cube epsilon naught H equals to K.
Yeah.
And the numerical prefactor was 16 by 3 pi cube.
Yeah. I think that's correct.
Answer. Hopefully.
And B4. For CY5 molecule, D is approximately 2.5 EL. Evaluate the mean fluorescence lifetime of the lowest excited state of the CY5 molecule, tau CY5, which is reciprocal to the rate of its emissive transition to the ground state. So just take reciprocal and evaluate.
Yes.
I don't really want to plug in.
Yes, I also don't really want to evaluate this.
Yeah, I guess you can just leave it like this.
Yes.
Okay, then you can do the next part, part C1. And this part is not directly related to parts A and B. Here we will study the collective behavior of bosonic particles. Bosons do not respect the Pauli exclusion principle, and at low temperatures or high densities experience a dramatic phenomenon known as Bose-Einstein condensation, BEC. This is a phase transition to an intriguing collective quantum state. A large number of identical particles condensed into a single quantum state and start behaving as a single wave. The transition is typically reached by cooling a fixed number of particles below the critical temperature. In principle, it can also be induced by keeping the temperature fixed and driving the particle density past its critical value. We begin by exploring the relationship between temperature and particle density at the transition. As it turns out, estimates of their critical values can be deducted from a simple observation. Bose-Einstein condensation takes place when the de Broglie wavelength corresponding to the mean square speed of the particles is equal to the characteristic distance between the particles in the gas. And C1 is given a non-interacting gas of 87 rubidium atoms in thermal equilibrium. Write the expression for their typical linear momentum P and the typical de Broglie wavelength lambda dB as a function of the atom's mass m and temperature T and physical constants.
One thing in this question I didn't understand is Bose-Einstein condensate takes place when the de Broglie wavelength corresponding to the mean square speed of the particle is equals to the characteristic distance between the gas. Then what is the characteristic distance?
I guess like mean free path. I don't know.
Okay.
Yeah, I think it's mean free path.
For C1, I don't think we required that.
Yeah. I guess you can just equate average kinetic energy to like p squared over 2m, and that'll like from equipartition theorem, and then we'd get the momentum. Then just find de Broglie wavelength from that. So like 3/2 kV T is equal to p squared 3 kBt. So lambda, that should be it, right?
Yes, I also think that.
Okay. And then
C2. Calculate the typical distance between the particles of the particles in the gas L as a function of particle density. Is this typical distance same as critical distance or different?
uh, not sure. Maybe it's just like average distance.
Okay. Calculate the typical distance between the particles in a gas L as a function of particle density N. Hence, deduce the critical temperature Tc as a function of atoms' mass, their density, and the physical constants.
I guess typical distance just the de Broglie wavelength.
Yes, it can be.
Yeah, that would make sense because it says de Broglie wavelength corresponding to mean square speed is equal to characteristic distance. Yeah, then we'd use that.
But what will we do of the particle density N? N is number of particles per unit volume.
So n over v. Oh,
I think they should define a typical distance.
yeah.
Typical distance.
If you say typical distance is d, then oh no, I don't know actually.
Now you are increased. I have no idea what is the typical distance here mentioned.
Anyways, I guess you can just since I guess you could say it's the same thing as de Broglie wavelength, and if typical distance is d, then that, and I mean you express in terms of particle density. Particle density. I guess like if there's a cube and each length of the cube is d, and there are n particles, and you can replace v with d cubed, so n is equal to
So
d.
D is here typical density or de Broglie wavelength. I mean typical length or
Maybe they're like the same
okay.
scale. Yeah, like maybe. So that we can
So
approximate.
we can write it as L.
Okay.
So but we also don't know capital N.
Yeah. Well, I guess n is proportional to d minus 3. So,
Or we can assume N to be 1. For one particle, the volume required should be typical one.
oh yeah, for one particle, then that would make sense. Because it's uh yeah, it's a typical distance. So there would only be one or two particles in that box.
Yes. And also you first told the mean free path. It will also be approximately this only. So
Yeah.
by taking N1, we can directly get 1 over D cube.
Okay. And then we can equate to this, or just substitute lambda from what you got before.
Yes, we can substitute here. So this is, I think we can conclude C2.
Yeah. Okay. We can go to C3 then.
To realize BEC in the lab, the experimentalists have to cool gases to the temperature as low as Tc equals to 100 nanokelvin. What is the particle density of Rb gas Nc if the transition takes place at such a temperature? For the sake of comparison, calculate also the ordinary particle density N0 of an ideal gas and at a standard temperature and pressure STP, that is T naught equals to 100 Kelvin and P naught equals to 10 to the power 5 Pascal. How many times the ordinary gas is denser? Shouldn't the Bose-Einstein gas should be denser because they have told that it is very dense.
Yeah. Since it exists at like roughly like 0, yeah, it should be very dense.
But here they as we can use as negative 10 to the power negative index to find denser how much. You may assume that the mass of the atoms is equals to 87 atomic mass unit. So
Okay.
this is just value putting.
Yeah. So like ideal gas law versus what you got in C2.
Yes.
Okay, then we can just go to D, part D.
Yes. You can read this.
Okay, one sec. The first Bose-Einstein condensates were produced back in 1995, and since then the experimental work has branched out in diverse directions. In this part, you'll investigate one particularly fruitful idea to load the condensate into spatially periodic potentials created by interfering a number of coherent laser beams. Due to the periodic nature of the resulting interference patterns, they are referred to as optical lattices. The potential energy V of R of an atom moving in an optical lattice is proportional to the local intensity of the light. And in your calculations, you may assume that V of R is equal to negative alpha of the average value of the electric field squared, and RMS E squared. And here alpha is a positive constant, and the angle brackets indicate time averaging, which eliminates the rapidly oscillating terms. The electric field produced by the ith laser is described by E of I equals E sub 0 I, epsilon I cosine of the k of I dotted with R minus omega t, with the amplitude E sub 0 I and the wave vector k of I and the length polarization vector epsilon I. This looks pretty hard. Your task is to study triangular optical lattices that are produced by interfering three coherent laser beams of equal intensity. A typical setup is shown in figure 2a. Here all the three beams are polarized in the z direction and propagate in the xy plane and intersect at equal angles of 120 degrees. Choose the direction of the x-axis parallel to the wave vector k of 1. So d1. Using equations 2 and 3, obtain the expression for the potential energy V of R as a function of R equals xy in the plane of the beams. And the hint is the result can be neatly expressed as a constant term plus the sum of three cosine functions of the argument B of I dot R. Please write your result in the form and identify the vectors B of I. Okay, that's a lot.
What is the wave vector K1 vector?
I think it's like, what is it? What's the units? It's like it's like the direction where the wave propagates, I guess.
Okay. So we take a dot product with R vector. And subtract. This is very confusing.
Yeah. Like that's the equations 2 and 3. I can write them down.
So in this question, they are throwing laser beams to the particle and then seeing what is happening. I mean atom. They are throwing laser beams to an atom and then studying the motion of the atom. Am I right?
Yeah. Yeah, I think that's what
So
it is.
this V of R is potential energy of the atom, and this E is the electromagnetic function of that wave. And we average over time and make it as a function of only distance.
Well, I guess the first thing is to find the total electric field at the point where all the waves coincide.
Yes. So it would be, wait a minute. What is this term written E0I?
It's the amplitude.
Okay. So we have E0I. We can combine E0I and epsilon I to only this. So we don't have to write everywhere. K1 vector dot R vector minus omega t.
I guess you can write
Here
it as
R vector, what?
I guess you can write it as a sum.
Okay, yes. Some. Here R vector would be same for all, right?
Yeah.
Okay, we have
So
we sum square into negative alpha. But to square we have to expand this. So we would get cos square terms for this. I1 cos square terms plus I2 E2 cos square term and E3 cos square term, and then we will get E1 2E1 U2 cosine of this into cos of another, and so on for this also. So average of cos square is 1/2 over whole time period. So we can write directly half.
yeah.
Is even E2, E3 same or different? E0, I mean E0 I.
Judging from the problem, I think it's the same.
Okay. So we can do this as 3/2R into E. 3/2 E plus the average of this. Okay, for average, I think we can write 2 cosine into addition form. So we can get even E2 cosine of addition of both. That is K1 plus K2 vector R cap minus 2 omega t plus cos of k1 minus k2 vector times r. Okay, this would average out to be 0 as this is cost term and it will be whole period. So we have this. So we have 3 over 2 e plus e1 e2 plus e1 e2 cos k1 minus k2 vector dot r vector plus e2 e3 and then plus e3 e1 cos.
That
This should be your answer.
okay, and then we have to write in terms of the hint.
Given cosine function arguments. Yes, we are getting 3 cosine and I guess b is k1 minus k2.
Yeah, or k3 minus k1 or k2 minus k3.
Yes,
Yeah, okay, then it should be good.
yes. But we are also getting additional 3 by 2 e. And here here is e into epsilon I. So we have to substitute back.
Yeah.
Okay, so is there someone watching? No. So let us continue to part D2. The resulting potential energy has a six-fold rotational symmetry. That is, the potential distribution is invariant with respect to rotation by a multiple of 60 degrees around the origin. Provide a simple argument to prove that this is indeed the case.
Okay, wait.
So we had K1 here, K2 here, and K3 here. So they are asking us to rotate it by 60 degree. That would become K1 here, K3 here, and K2 here. And let this point be R vector.
Okay, so k1, k2, k3 are just like the same thing, but just relabeled.
No, but the same thing is this dotted line. We can prove 120 degree by that, but 60 degree, I think that is, we can't do that.
Then
We have the difference terms, so can we use it as our benefit?
we can use the vectors that we had from last time. So like bi, so like b. So there's b1, b2, b3, and then when you rotate them, the vectors are going to be mapped the same way. I think. I'm not sure.
Can you prove it? Also, can you go to another slide? So this is becoming very messy.
I can't actually open any more slides. We have to go back.
Oh, so there is a 20 slide limit, I guess.
We can use this slide.
Yes.
Okay.
So yesterday we completed before 20 slides.
Yeah, we had like 19 or something.
Oh. So we have K1 vector like this, K2 vector like this, and K3 vector like this. And we then rotated by 60 degree. So we have now K1 vector like this, K2, K3. So the difference would be, we can make a parallelogram, and difference would be like this.
Yeah.
No, like this, sorry. And for this, it would be this. Wait, this is becoming a lot more messier. I should rub and draw with another color. Difference here would be, yes. And for this, it will, okay, the difference is same. The difference has an angle of 60 degree only. So if we rotate, we can get the same triangle.
Yeah. Yeah, then the behavior must be same. And then on to D3. The above observations of symmetry simplifies the analysis into the two-dimensional potential distribution V of R. As shown in figure 2b, a regular hexagon has a symmetry lines that respectively connect opposite vertices and midpoints of opposite edges. Therefore, in our situation, one does not need to produce and study the two-dimensional potential plots, as many insights can be deduced by focusing on the coordinate axes x and y that run along the symmetry lines. Okay, I didn't really get that, but I'll just read the part. Determine the behavior or the potential V of R along the coordinate axis, i.e. determine the functions Vx of x, which is congruent to Vx0, and Vy of y, congruent to V0y. Identify the locations of the extrema of Vx of x and Vy of y as functions of a single argument. As these functions are periodic, please include in your list only one representative from each family of periodically repeated minima and maxima. Okay, that's a lot to take in.
So can we use the diagram and assume that K1 equals to I cap, K2 equals to, I mean, some K factor into I cap, and K2 equals to root I by 2 plus root 3 by 2 J cap whole into K, and K3 equals to I by 2 I cap minus root 3 by 2 J cap whole into K.
Okay, can you write that down?
K1 equals K naught times I cap, K naught times I cap by 2 plus root 3 by 2 J cap, and K3 equals to K naught I by 2 times minus root 3 by 2 J cap. From
Oh,
the diagram, from this diagram this is not the exact diagram, but from the diagram in the question I am assuming this.
Yeah, yeah, okay, that looks right. Then we just add those, right?
If they are equal in magnitude, then only. Because otherwise, the function, finding the function in x and y won't make any sense, as R vector would be simpler if we don't assume the values.
Okay, so then we use uh, the formula from D1 that we got, and then we had to find the minimum from that with the new k vectors defined. Anyway, I can go back to that slide. Let me take a picture.
Also, they have told us that it is a regular hexagon. So I guess we can assume K naught to be same for all the three. And if this is the case, then it would be very easier to do that.
Yeah. K1.
So we can substitute directly values of K1, K2 and K3 here. And this was K1 minus K2 and so on. It was the difference.
Oh, K1 minus. Oh, yeah. Okay, so then I need some more space then.
You should write it in the bottom. You can get line. Sorry, I think I got disconnected.
Oh, I didn't notice.
Yes, so we can substitute K1. Oh, you didn't write R. So we can directly substitute K and do the dot product. So for x direction, we have here K naught into I by 2 x. Here we have 0 and here we have x k naught I by 2. S minus would be cancelled by the cos. So we get 2 times cos of this for x direction. So maximum would be 5 by 2 and the minimum would be 1 by 2 times this. And for y we have k1 minus k2, that is root 3 by 2, root 3 by 2 y k naught. We have here root 3 y k naught and here also root 3 by 2 y k naught. Oops, this maxima would be hard. Plus this is 2 times. Or we can apply cos 2 theta formula for this. So this will 2 cos square theta minus 1. So 1 we can subtract, so we can get 1 half. So we have to find the maximum of this quadratic equation. And it will be in minus 1. So we can plug in minus 1 here. So we have minus 2 minus 2 plus 2 plus 1 half. So we have 1 half here. And if we plug in 1 half, then we have 5 by 2. So for y also we get 1 half and 5 by 2 times this quantity.
Okay, looks good. So, okay, so then what's the final answer?
Wait, let me see what they have asked. They identify the location of the maxima of the extrema as a function of the single argument. As this function are periodic, please include in your list only one representative form of each family of the periodical repeated. Oh, so we have to find where is the maxima, not what is the maxima.
Oh,
So that so we have maxima at plus 1 half. So we have k naught. Wait a minute. Yes. So we have k naught x equals to 0 for the maxima and is this addition? Okay, did a mistake. This is subtraction. So this would be 3. So we have 3x k naught by 2 equals to pi for minima. This is for maxima. This is for minima.
so
And
then,
similarly for y, we have uh, 0 y equals to 0 for maxima, and root 3 by 2 y k naught equals to pi for minima.
Okay.
So this should be the answer.
Then we can do D4. Review your results in the previous question to determine the actual minima of the optical lattice.
What?
Oh, we can do D4 now.
Okay.
Alright, I can read the part before.
We are interested.
Oh yeah, you can read it. You can read it.
What? Sorry, I didn't. Yes.
You can read
We
it.
are interested in determining the we are interested in determining the locations of so-called lattice sites. That is the maxima of the full two-dimensional potential V of R. The obtained minima of the single argument function Vx and Vy, and identify their suspected position, but still have to check to eliminate the saddle points as shown in the figure 2c. When studied along the single line, saddle point may disguise as minima, but they are not.
Okay, and then review your results in the previous question to determine actual minima of the optical lattice. Identify all equivalent minima nearest to but not coinciding with the origin. What is the distance a between the nearest minima? In other words, the lattice constant of our optical lattice. Express the answer in terms of the laser wavelength lambda of laser. So that we kind of did that before.
Okay, so I guess they are asking the both when both the minima coincides to get the absolute minima.
So I guess the first minima is just 0, 0.
What, that would be maxima. Okay, this is minus, so minima.
Then
And then this is increasing in multiple of 3 over 2, but this is only increasing with the multiple of root 3 by 2. So we would get a factor of root 3. But how would we calculate the LCM of root 3 and 1?
um, I'll see it. So that would be. Wait, what? That doesn't make sense actually. What?
I think I didn't understand the question.
Yeah, me too. I guess you can look at the minima that we had. So you had minima of x equals 2 pi over 3k. And then okay, so then
no, that is maxima, so minus sign. So I have to reverse all this. This is minima, this is maxima,
oh
and
okay,
so on.
then we can forget about
So we have to make it as a multiple of 2 pi. So 3x over 2, sorry, 3x k naught over 2 should be multiple of 2 pi. So x should be multiple of 4 pi by 3. X here is a multiple of 4n pi by 3, and y here is multiple of 2 4 pi n over root 3. But what can we do, as they are independent variables and independent solutions?
yeah, like the actual minima would be both of them together. So then I guess the nearest minima, since both of these are like functions of
Okay,
n.
this is x this and y equals to 0, and this is y x0 and y this. So we have to find the point where the actual dot product becomes 5 over 2.
Yeah. So we can go back
Yeah,
into
I think, yes, to get more space. This is becoming very clumsy.
we can just
And
erase
we
this.
can erase this. This is dimensional analysis.
Oh, okay.
I clear. I did clear also. Did it erase all the drawings from previous slide also? Or yes, this slide. Yes, this feature is nice. So we have K1 equals to I cap over 2 plus root 3 by 2 J cap into K. K2 equals to minus I over 2 plus root 3 by 2 J cap. K. K3 equals to, I can write K3 here. K3 equals to minus I over 2 minus root 3 by 2 J cap. So we have 3 over 2 plus cos of this minus this, that is I times x. Wait, this is I only. This is, so this is 3I over 2 x minus root 3 by over 2y, and
Okay.
after taking up I can put eliminate, and I am ignoring the constants k and all that,
Okay, sure.
plus cos k2 minus k3, that is 0 for this, and root 3 over 2, 2 would cancel out, y, plus cos of k1 minus k3, that is 3x by 2 plus root 3 by 2y. So now we have to find complete for x and y where we can get pi over 2. Means we can get this quantity as 1
Yeah.
for the values. So I think partial derivative will help.
Yeah, I was thinking that too.
So differentiation of cos is sine negative root 3 by 2y, negative will cancel out, and root 3 over 2 plus differentiation of sine is negative sine root 3y
Root
into
3.
root 3 minus sine of root 3 over 2y root 3 over 2 equals to 0. So we can cancel out root 3, and we can get sine of root 3 by 2y plus sine of root 3y plus sine of root, this can be 2 times equals to 0.
So then the minima are 2
We
pi
can
over
write
pi
this
3.
2 sine root 3 by 2y cos root 3 by 2y. So either sine root 3 by y equals to 0, or uh, cos root 3 by 2y equals to minus 1. This is the condition from y differentiation.
Yeah. So we can have
Now let us differentiate y x.
y is equal to 2 pi over root 3. Or y can be 0.
Yes, y can be 0, uh, or root 3 y over 2 can be multiples of pi, all the multiples of pi.
Yeah, and pi. Then we are looking for
For
minima on
x we have
losses.
root 3 cos 3x 2 minus cos 3x by 2. Oops. I plugged x equals to 0 while partial derivative. I messed up.
Oh,
And also this would become the same thing as the one we did above.
Yeah, y and x should be symmetric.
No, because we have assumed this K like this. If we rotate by 60 degree, it won't be symmetric.
Oh wait, yeah.
This calculation is too clumsy. I have a strong feeling to put this in the Desmos and equate to 1. We can find all the.
Honestly, like, yeah, this problem is just minimizing our potential function.
Yes. Or might be we are doing something wrong that has also high chances,
Yeah.
because I don't understood the fourth question very well.
Yeah. Let me uh, try to do this on paper. 1 second. Okay, what are the minima that we found before for part D3?
In the next slide,
Wait,
or I think I rubbed it.
is it gone? Oh no. Oh, right here.
Yes.
Okay, let's just say that I found one minima is going to be the actual minima. Oh, it'll be like at
No,
x.
for this way, I think we have to find maxima because there is a minus sign as a factor.
Maxima. Wait, why? Wait, why?
Because we have minus alpha E naught square.
Oh yeah. Then then this only x equals 0 and y equals 0.
So these are minimas only. These are minima and these are maxima. I have written it opposite because at that time I didn't knew about this minus sign. These are all opposite. Minima, maxima, minima, maxima.
Okay, honestly, I don't really know anymore. This is getting kind of confusing. Do you guys want to do the next part and then come back to it?
Yes.
Okay. Okay, I don't know. Clear drawings. Clear
Okay, we have only one part left. Nice.
Yeah, I guess you can just do this part.
Yes.
Okay, so D1.
Also, we have exceeded the time limit of IPHO.
I guess that's fine for a live solve because like.
Yes, we are trying all the questions again and again.
Yeah.
If we don't succeed.
So,
Charge neutrality.
you can go.
Okay. Charge neutrality of the ultra cold atoms suggests that their interaction between relevant only become relevant only when the two or more atoms occupy the same site of an optical lattice. However, the experimentalists are also able to explore setups and sustain long-range atomic interaction. A possible approach relies on the creation of so-called Rydberg atoms that are physically large and featured other exaggerated properties. Rydberg atoms are excited atoms with one electron promoted to a state with a very high principal quantum number n. The size of Rydberg atom can be estimated by calculating the radius of classical orbit, circular orbit of that electron with orbital angular momentum nh, where h is the reduced Planck's constant. Calculate the value of n that corresponds to the radius of Rydberg atom comparable to the wavelength of laser light 380 nanometer. Give your answer in the terms of lambda laser and physical constant and find the numerical value. For this question, do we have to calculate the Bohr radius? As they have said, classical circular orbit of electron and angular momentum also given. So
Yeah, I
NH
think.
is 2 pi r.
So equate angular momentum to nh bar.
Yes, and mv square by r equals to k e
Over 4 pi epsilon naught r, or over r squared.
and the z of rb
Yeah.
rubidium z times e square by r square. So we can substitute the value of if we from this, so nh by 2 pi m by r implies m n square h square by 2 pi square m by r square equals to k e square z by r gets cancelled out. We have r equals to k e square z. Wait, I think I messed up.
Or is
We have r equals to n square h square by 4 pi square m times 4 pi epsilon naught e square z. So 4 pi cancels with this.
yeah, so then e squared over pi m.
But I don't get what is comparable lambda laser. What that? What does they mean by that?
I think it's just r. Yeah, because like bore radius would be the same as the wavelength.
Okay, so we can directly equate them to
Yeah,
lambda laser
yeah, and then you would find n
and
from
then
that.
find n. Okay, that would be just calculation part.
Yeah, so n is like square root pi m e squared z lambda over h squared epsilon. Oh god. Yeah, I guess that's it. We can go back, but like to this part. But yeah, I think that's the entire paper, right?
Yes. So finally, we have completed whole IPHO paper.
Okay. Should I end the live stream then?
Yes, we just we were not able to solve two parts in this paper.
Yeah, so
One capacitor one and one this last one. If we assume that all the parts we solved are correct.
yeah, so we that give a pretty high theoretical score.
Yes.
So other than T1, D1, and then T3, D4. Okay, well, yeah. Thanks for coming to the Livesolve, and yeah, see you next time.